So the funky thing is about functional, obviously, and we are going to talk about adding functional to your OOP code bases. That's, I think, that's something I'm doing a bit differently than most talks about the topic. I know you got millions of lines of code of OOP code, and I don't think that's going to change. I'm not telling you to throw any of this away. That's not realistic. But I'm going to talk about how you add functional concepts to that and get some advantage out of that. And I think I mentioned C# in the abstract. Here I don't even mention C# in the title. Most of what I'm talking about is applicable to any multi-paradigm language that supports OOP and functional. So while the examples are in C#, you could similar things in TypeScript, in Kotlin, and a bunch of other languages. So what exactly are we going to talk about? First, we're going to talk about the order of functions. Yes, they have orders. They're not all created equally. We're talking about what pure functions are. This, I think, is what the first thing that starts scaring people away, because that's what the functional people usually like to talk about, but we have to cover it. It's important to understand and what it means, when to use it. And with those two defined, then we can try to define functional programming. I say define because this is more difficult than you'd think. When I started preparing the slide deck, I thought, oh, this has been around for decades. Surely we as a field have a definition of functional. No, not so much. Well, we're going to do our best. Then closures, that is probably something you use on a regular, if not day-to-day basis, but to make sure we're all on the same page. We're going to revisit what they are and then see how those relate to functional programming. And then kind of the meat of it. Until that point, it's somewhat theoretical, might feel in part like a computer science lecture almost. Then we're looking at how do you apply this in the real world. And this is actually based on code I've actually written on the job. And then I got a couple of suggestions for the resources for you to look into if I hopefully convinced you that this is worth investing your time in, what to do next. But before we start, can I please get a show of hands? Who here does functional programming already? And I mean this very loosely. Do anything related to functional programming on a somewhat regular basis? Got 1, 2, okay. Well, it's an intro talk. This makes sense. But let me ask you this now. Again, show of hands. Who here does this? Who writes links queries and does your wheres and your selects? Yeah, that's pretty much everyone. So guess what? Those methods here, those are actually functional. They don't happen to be purely functional. Point being, you're halfway there. You're already using functional APIs. I wouldn't go as far as say that makes you a functional programmer already, but you're halfway there. Let me push you over the finish line. Get the rest of it. Okay, order of functions. And we start with the first order. First order sounds like maybe the greatest, the best, the highest. It's actually the lowest. But fortunately, it's also the one I don't need to talk about too much, really, because this is what you're used to and what you do use on a daily basis already. Those are all your functions that deal with data. So they take data, your value types, primitives, structs, objects, reference types. They can return any of those. They could also be void returning. Again, this is a bit computer sciencey, right? System.void is actually type in .NET, none you can use directly, but you can think of conceptually, well, you have a void instance token, whatever you're returning to the caller. Similarly, if you have an empty parameter list, it's an empty set. That is still data in a sense. So all of this is first order. You know this, don't have to talk about much more. So what about second, third, fourth order? There is none. There is only higher order functions. So it's either first or higher. And well, what does that mean? How is this different? And higher order functions do at least one of two things. One, they may take functions as arguments, like your link, for example, like you select. So you pass in an enumerable of tsource, some sequence of elements you want to process, and you also pass in a func of tsource and tresult, something to do with every single element in that sequence. The other example I have, so this is from the .NET framework too, is the lazy class. Once in a while, you might have a value of interest that is really expensive to compute. And maybe you don't always need it, but when you do, it's not just once or twice. You need it in a tight loop, so it makes sense to compute it once and cache it at the point where you first need it. So lazy lets you do this, but of course that means when you create a lazy, it doesn't have the value yet. That's the whole point. It's deferred evaluation. So instead, we're giving it a value factory, a func of t that, when called, will produce some value of type t, and then the lazy can just cache that and keep returning that. So that's one thing. The other thing, a high-order function might return functions. And we're going to see more of this. I want to stick with examples from the .NET framework, and then I end up in code generation. I apologize for this. But there's still good examples, I think. So one is from dynamic method.createDelegate. So the idea is I want to create actually a new method at runtime. Dynamic method lets me emit some IL, and at some point I say create delegate. It actually compiles this to actual blob of IL and gives me a delegate pointing to this new function. The other thing is expression of tDelegate. That's derived from lambda expression, so I can set up a lambda expression in abstract syntax tree at runtime to define some piece of functionality, and then I say compile, and again I get a delegate back. And of course, a function might do both of them, and we're actually going to see an example of that. Not from the .NET framework, but this is what higher order functions are about. So they take or return function. Same as we do with data, but of course that gives us whole new possibilities. Now, this unfortunate topic, pure functions, because it's different, it's somewhat scary. So what are they? In short, they are deterministic. And if this were an actual computer science lecture, I would probably say, let's leave it at that, it's clear, but let's break it down. So for one, the output they produce only depends on the arguments, always. It does not matter what the rest of the state of your application is, your environment, none of this matters. It only matters what you put in. But also, they have no side effects. They don't change any global state, any outside state. Meaning, calling a pure function will never cause another function to behave differently, to return different results when you give the same arguments to that function. So this is basically the same idea as functions in mathematics. When you have a linear function, f of x equals 2x, this will always produce twice x. It doesn't matter what f of y does or what f of z does. It doesn't have an environment, so to speak. It doesn't have global state. Our pure functions behave the same way. Now, what are side effects? They fall into 4 categories, basically, and number 4 will surprise you, I think. It surprised me. That's why there's a slide just on number 4. So number 1 is, I already touched on this a little bit, mutating global state. Now, what's important here, don't think global variables. They actually exist in .NET. They're not exposed in C# in any way. Also, don't think public static fields. When I say global state here, that includes those examples. But really, it's global as opposed to local. So when you're talking about pure functions, anything that's not local to the function is global. We can't change any of that. Excuse me. Similarly, I can't change argument. This gets a bit more interesting, though, because this only applies if the change is visible to the caller. So if, for example, I pass in an object, I pass an object reference, I do anything with this object and change its state, that is obviously visible to the caller who gave me that reference to this object. With structs, it depends with my value types. If I pass them by a value, which is the default in C#, I'm getting a copy. And with the copy, I can do whatever I want. This is not visible to the caller. But if I'm getting it by reference, and I might just for performance reasons, for example, then of course, whatever changes I make are visible to the caller. I'm not allowed to do that. Number 3 is, to me, actually the most obvious intuitively. As soon as you do I/O, there's devices involved. There's other processes involved, the kernel, drivers, buffers of all sorts. So whenever you do I/O, you change state all over the place. Number 4, let's see if you're surprised. Who here is surprised? Exceptions. There is a side effect. And it took me a while to wrap my head around why that is. And I went to Stack Overflow, and there was debate between the more computer sciencey people and the theory behind it. But I think it boils down to this. When I thought about this, I thought, well, exceptions are about control flow. What does any of this have to do with state, right? So I'm saying, for an exception, I stop doing whatever I'm doing, some exception handler will pick it up, either in my application, or if mine does not have one, then it goes all the way down to the runtime or the operating system. Somebody will handle it. Actually, I got a hand up there?
Yeah, I wanted to ask about Rust result type. Because it can provide you a value on it or an error.
Let's save questions like this for the end. So this is a good question, but let's save this. Thank you. Well, back to control flow. So yeah, we got exceptions. We changed the control flow. But what is the state that we possibly might be messing with? And then I started thinking, how does control flow actually work on the lower level? And what hidden state is there? So when you think about branching, on a low level, you have branch instructions, and they might be conditional, right? You only branch when if statements get compiled down, if a value is 0, non-zero, greater than, less than. So that depends on state, but it still doesn't change anything. The huge exception here, no pun intended, other than exceptions, is calls and returns. Because we end up doing something with call stack. Now, this in and of itself doesn't make my function impure. That would not be very useful. So if I want to write a pure function, I can call other function as long as they are pure as well. Life is good. And again, throwing exception is a side effect, so they're not pure if they throw. And the problem lies here when I look at the stack frame a little bit closer. So there's three things. There might be arguments, there might be not because they're passed in a different way or because it just doesn't have any arguments, but this is one thing. On top, you got the local variables of that method that's running, and then you got the return address. So what's happening now when I throw an exception, it's not that I'm literally changing the return address, but I'm changing the effective return address. Because I'm saying, don't go back there, go to the first catch you find and execute that. Now that's the very technical explanation, but if you also want to think it in more practical terms and also take into account what I've said a bit earlier, you are now causing other functions to behave differently. Because as the runtime unwinds the stack, if that method that it's looking at doesn't have a catch at all, it's just going to get basically interrupted. Started doing some work, now we're throwing it away, it can't even finish. And of course, the first one that does have a catch, we're also messing with that and they're saying, okay, don't do what you originally planned to do, now resume execution where this catch is. So that's what makes this a side effect. So how do we make it easy to have pure functions? And a key aspect in this is immutability. So I'm not allowed to change more arguments if this would be visible to the caller. I'm not allowed to change anything else. I'm supposed to return things that are immutable too, ideally. So the way to do this, the easiest way, is to just deal with immutable data structures. The first point about this, you could theoretically say we're doing this by convention. Just say whatever we pass into our pure functions, that's never going to get changed again. And this is dangerous for a few reasons. So one thing, keep in mind, we're talking about the context here, object-oriented programming, and we're adding functional. So you're used to changing objects around all the time. And now you start having little islands in your code where you're not allowed to. This is easy to just get wrong, and there's two particular ways. One is when you actually capture variables in a closure. You might change those in between calls to that closure. That's bad. This gets even worse when you have multi-threading. So values could even change while our supposedly pure function is running. And of course, I'm still thinking if I should take this off or not, but I've seen this too many times to not leave it in. The cowboy coder. Somebody might just intentionally not do this, even though if you clearly said, we got some functional in here, it's supposed to be pure, don't do it. Now the good news is, if you're on C# 9 or later, we have record types that can be easily immutable. It's very nice syntax. It's easy to do. You have the with expression, so it's also very easy to say, okay, I got this immutable thing, now I want to change it in quotation marks. So I want a new one that has all the old values, but some things change. It's easy. Of course, if you're on 8 or earlier, you don't have this. You should still hand rule your own immutable data structures if you don't have anything available readily. Of course, you don't have with expressions, so the whole deal of creating a new one based on an old one becomes a bit more tedious, but that's what you would have to do pure. And last point, on returning. For purity, it doesn't really matter if what you return is immutable or not, but the whole idea of pure functional programming is that ideally everything that can be pure is pure. So I'm composing pure functions. So the output of one pure function becomes input to the next pure function. Of course, that should get something that's immutable. So it's kind of all in a sense. And then one thing to keep in mind, you need to be careful on hot paths. Of course, if you can't mutate state, if you always have to create a new object, that means additional mem copies that you would not have. Might not matter too much most of the time, but again, you have hot paths, performance critical areas of your solution, something to keep in mind. Now, why do this? This sounds tedious. It has all these rules, all these new concepts. Why do you want to do any of this? One is better testability. Now, I'm not saying it becomes trivial. In some cases it does, but all you have to worry about is now preparing your arguments to pass in, because that's the only thing that determines the output. That still might get complicated in a way, but you don't have to think about, oh, I need to have this state in the database and this state in the file system and this and that prepared outside the unit that I want to test. None of this matters. Pure functions can only be memoized, and I really hate this word, because I always feel like I'm mispronouncing memorized. And they're also conceptually very similar, right? This is about your function remembering values it's already computed. And this can be very useful when the computation is very expensive and you need it all the time. And the overhead of having a dictionary where you use the arguments as a key and then you cache whatever result you calculated, that might be much cheaper than keeping to recalculate. But the point is we always can do this because the output only depends on the argument. So we can just do this once and cache it. Thread safety, this is basically nothing shared, or what is shared is immutable anyway. So when I do things like processing lists, I still need to make sure that I call my pure functions in a thread-safe way, but the pure functions in of themselves, they don't care. They get the input, do something with it, and have deterministic output. The last point is a bit more academic in that it's not available in C#. I'm not sure if there's any language. Well, you can compile C++ to CLR, so that's a big exception. That's compile time evaluation. You can take this a step further when you say, okay, I got pure functions, the output only depends on the inputs, on the arguments. What if the inputs are all compile time constant? If you know the exact value of all arguments at compile time, the compiler can execute the code for you and just put the actual value into the binary. And I find this so fascinating, you should really watch this. It's from a C++ conference, but even if you don't know much or any C++ really, and there's a bit of assembly in there as well, it's very interesting to watch because what he's doing on stage in an hour 15 or so, he's creating a Pong clone in C++ for the Commodore 64. And I'm not much of a C++ developer myself, but when I first hear this, I think, wait a minute, you got all this runtime stuff and objects, and how can this run on a 1 megahertz CPU? How is that possible? There's a bunch of tricks that he's using, but one is compile time evaluation, because some stuff is actually executed at compile time, and poor Commodore 64 doesn't have to worry about it. Now, with all this said, we can now try to define functional programming. And if you start looking into this, you might find a quote like, functional programming is programming using pure functions that manipulate immutable values. So basically, the important concepts I've shown you so far, pure functions, immutability, program with that is functional programming. That's a quote from Grokking Functional Programming. You dig a bit deeper and maybe, I don't know, check Wikipedia. What does Wikipedia say about functional programming? And it says, well, functional programming is sometimes treated as synonymous with purely functional programming, a subset of functional programming. That's where it gets interesting. And to be clear, I don't think the first quote here is wrong. It is a definition of functional programming. And when you talk to people who do functional programming exclusively or mostly, especially Haskell, because Haskell is a purely functional language, they probably go with this definition. But we're getting a sense, well, this might not be the only one. And then similarly, there's an article in Wikipedia about purely functional programming. It reiterates it's about basically doing math in your programs. Okay, how else can we define this? There's a quote from Functional Programming in C# that says, at a high level, it's a programming style that emphasizes functions while avoiding state mutations. I like this a lot. So it's talking about not everything has to be immutable, but it should be immutable. Try to avoid mutating stuff. And I think it makes a lot of sense, but requires context. Because if I take this literally, we're just emphasizing functions, these all of a sudden become functional programming languages. Anybody recognize these? Yeah, no? Those are Quick, Basic, and Pascal, back from the good old DOS days. They're what's known as procedural programming languages. And procedure in this context is also known as a routine, subroutine. In OOP, we call it a method. A general term for the idea is a callable unit. A piece of code that does something useful, I define it once, and then I can invoke it from all sorts of places in my code base. And you might now go, duh, of course. In the late 50s, early 60s, this was groundbreaking. This was new. And again, the definition I just showed you, that would say these are functional programmers. No, they're just procedural programming languages. Okay, going back to Wikipedia, what else does that tell me? It says, well, functional programming is a programming paradigm where programs are constructed by applying and composing functions. This one I also like a lot because I think it's highly accurate and condenses the idea in one sentence, but it's not very accessible unless you've already read quite a bit about this topic, which brings me to the definitive definition for this talk, because it's mine. And I'm saying, okay, functional programming is programming in a language that has first-class functions. So we can treat functions like we treat data. We can use them as arguments. We can use them as return values. We have closure support. And we use this to define and compose higher-order functions. And everybody here uses LINQ. So we already have the using of this down. Now we want to create our own and compose them into more complex functionality. Before we dig into closures, quick word about pattern matching. Because when you talk to the functional people, they are all into pattern matching. And pattern matching as a feature is great, love it. It's very expressive. It's often much shorter than all your if-else constructs you would have to use otherwise. But in my view, this is absolutely not required for functional programming. So let's talk about C# for a second. Just because a language is functional or also functional doesn't necessarily mean it necessarily supports pattern matching. So C# didn't start until 7, and even before 7, like I think starting in C#3 probably, you can do functional programming just fine. It is a common feature of functional first languages, definitely, which I think is a reason why in that space, talking Haskell, Scala, F#, this is very natural for them to use. This goes so far that if you look up pattern matching on Wikipedia, there is a disclaimer that says, this article is about pattern matching in functional programming. Okay. Ironically, though, then maybe you go back to the functional programming article and look what that says about pattern matching. That's what it says. It doesn't even mention the term at all. So just so much on that. Pattern matching, very common, very useful, not strictly necessary functional programming, or shouldn't I say strictly, not necessary. Let's talk about closures. What is a closure? And I'm sorry, again, it gets a bit computer sciencey here. It's a local or anonymous function that captures free variables, especially the free variable. What the hell is that? It is just a variable that's essentially not local. That's defined somewhere outside of that function, and that without closure support, I would not have any way of accessing. What's important here, this is orthogonal to order and purity. So a closure can be pure or impure, and it can be a higher order function or a first order function. It has nothing to do with that. The key here is I'm capturing variables, these free variables. And this is useful because it allows me to create a function at runtime that I want to pass to some other function, like one of those LINQ methods, where I need a value that's not known until runtime. I can capture that and then have a closure with the right signature to pass to select, where, and all these others. So let's look at an example. I have this create increment decrement function pair method that returns a tuple of two funcs of int and takes an increment. The idea is here I have a pair of functions. They operate on the same variable and they increment and decrement it by whatever increment you set, just to illustrate this concept. Otherwise, it's pretty useless. So in this function, I have a val. I initialize it with 0, and then I say return two anonymous functions. One just says val plus equals increment. The other one says val minus equal increment. I call this, and then I have funcs. And one thing to notice immediately is, of course, well, A, this is impure, because I have this val that I keep using and I keep mutating. But also, normally, val would go away if I didn't have the closures. Right? At the end of create incdenc func pair, this is hard to say. It's out of scope, it should go away, but it keeps around because I've captured it in two closures. And then, of course, if I keep calling this and just print out the value, it works as advertised. Increments and decrements by 3 in this case. So we can extend the lifetime of variables. We can use them. I can also do something like this, and this is more real world now. Say I have login records, and they're a bit simplified. They just have a timestamp and username and just a bool if the login worked or not. In the real world, I think you want a little bit more. And let's say I want the last 24 hours. And the right way to do is first I need to say, okay, what is my exact cutoff? Because if I don't calculate this first, I have to recalculate this all the time. Also, I'll have a drift at some point. So I calculate this first. And then I just say logins where, say L goes to L.timestamp greater or equal to min timestamp. Now again, we have a closure here. We captured min timestamp, but in this case, this one is pure now. Why? Because min timestamp does not change anymore after I create the lambda. The closure. It is a lambda, but the closure, after it's being created, what it relies on is not changed anymore, so this closure will always give you the same answer with any given input. Now, we finally arrived at the more interesting part, in a sense, actual examples. How to use any of this? Why is this useful? And first, let's talk about don't repeat yourself. It's really handy for this as a concrete example. Let's say I got some session records. I got speaker, I got the title, I got 2 records. Actually just 1 record here, but I want to print it twice. I want to print it as, or output it as JSON. I want to output it as a text file. So far, so good. So I might write something like this. I have a write to JSON file method. It takes a file name and a session. It opens a file stream, calls a serializer. I get some JSON back. And just for the pattern, it's a bit silly as an example. At the end, I set a read-only flag. So I have these 2 steps and this thing in the middle where in the first one I'm doing JSON, in the second one, the first and the last line of write to text file are the same, but in the middle I now say, okay, I need a stream writer, and I just have some arbitrary plain text output there in some form that I desire. I can run this, it does exactly what I wanted it to do. What's the problem? This is the problem, obviously. And a real-world example will be longer. That's why I don't have one. It had to be simplified to actually fit on a slide. I get code duplication here. And in this case, there's this rule of 3s, I think, where I'd say this is still fine. But maybe now you add XML and some binary format, and you keep doing this over and over again. It's bad at some points. What can we do? And if I'm sticking with my OOP, I'd say, well, there's a pattern for that. It's a template method pattern. This basically says, okay, we have some common functionality. We're going to put this in a base class and have what's known as a template method that has the common code and it has calls to other methods that are protected that implement this use case specific part. In this case, writing JSON, writing text file. And then I can derive from that and just overwrite primitive 1, primitive 2, and that works. There's nothing wrong with that. I can now say, okay, I have an abstract class, file writer of T, And again, in my create new, the first and the last line is exactly what you've seen before. I got a file stream, I set an attribute, and then, but in the middle, I call a protected abstract method that will then, in a derived method, have the concrete way of formatting this, like formatting as JSON, formatting as text. Okay, so this is great. What if I want to do this in a functional style? And that would look a little bit like this. So the create new file is pretty much the same as in the OOP solution. The difference, though, is I can't derive. I have a function. My function has to take a function, action, file stream action, that then does write the JSON or the text. But this is not that much difference. Quite frankly, if you had to choose between those two as is, to a large extent, this is up to preference, style, maybe your team agreements, how you want to write code. That's fine. So why I'm telling you this, because we're going to make it interesting. What about optional exception handling? So maybe this is something that's not critical. Maybe I'm writing some, I don't know, telemetry data or something that it's not critical when it doesn't work. I want this handled immediately when it happens. And maybe I also want to know about it, write it to trace output, console or something. But I don't want this to trickle down further in my call stack and hit a lower level exception handler. So again, let's look at the OOP solution. I could say, okay, let's create an exception handler of sort. I omitted the interface definition. The idea is just I have an interface with a handle method. It gets some sort of exception. I will throw in a bool to indicate if it should be rethrown or not for good measure. I can create handlers of this and then extend my actual file writers to then also take a handler. Okay, there are two slides that don't work. Don't ask me why. I have no idea why this is happening. This is extremely weird. Okay, let's just resume here, and apologies for the delay. This is actually the solution you have already seen, and now my question, maybe somebody has an idea, wants to shout it out. So how do I add this optional exception handling to my functional solution? Any ideas? You already asked about Rust, so you probably know how to solve this properly, but okay, hit me. Mm-hmm. Yes, so he says, let's pass the exception handler to our function as an additional argument. You could do this, and quite frankly, when I started doing things like this, this was also my first impulse coming from OOP, but there's a better way. So the answer really is, what you change here is nothing. Nothing needs to change here, because let's think about what you really try to achieve. And I had the hint here a little bit. I have a piece of functionality that does something. It doesn't really matter what it does. In this case, it just happens to write files. I want to have an optional exception handler for that, whatever this may be. So in functional, I can do this. I can just create a function I call with exception handler of t, where t is some sort of exception. And then this takes an action, and this does take an handler, because how to handle is still up to the caller. But I solved this with composition. So I'm getting the original code, I try that, and then call my exception handler if that failed. And now it's up to the caller. The optionality comes in. The caller decides, do they want to compose the function they already had with exception handler or not? Problem solved. And I'm running out of time because of the tech issues. I have to run a little bit through it, so I apologize. Second example, generators. And that's cheating a little bit because technically that's not OOP. But I think yield return is pretty widely known and used at this point. I should be okay. And I need to generate an infinite sequence of date times. And the infinite comes in conceptually. How do you deal with infinite sequences? But also to cheat a little bit. Yes, this will overflow eventually. But I don't care about the year 10,000. Let's just pretend this doesn't overflow, just to make our lives a little bit simpler. And the one way you can do this is very simple. You have a method here, create enumerable, that gives you an enumerable of date times. There's one little check if your interval makes sense. It has to be at least 1. Okay, fine. And then it's just a while true. Again, we're pretending this is infinite. And we just keep calculating the next value in the sequence after the current one. Return the current with a yield return. and then do this over and over again. Works. And the way I use this is a bit ugly in that, so I can't for each over this, or for two reasons. A, it's infinite, I would never return, but also the context here was actually calculating delivery times from messages I want to send out. So I'm already for eaching over something. I can't for each over this as well. I can make this a little bit nicer in that this whole two-step process, move next and current, I can just create a little extension method. I've omitted the actual extension method, but one an I enumerator of t, then just have a get next that does those two steps. And if I run this again, it works as advertised. And again, which one you prefer, largely up to you. Again, if you're on a really hot path, you might prefer the functional one because it does not have the overhead of the iterator. So if you're really squeezed for cycles, that might be a difference you care about. Otherwise, up to you. I got ahead a little bit here, because that's the functional one. And as you see, I inverted here when I calculate and return, but it's still the very same idea. It just doesn't give you an enumerable, but a func of datetime. There's a little check for the interval, and then I just say return a new function, and I remember the start, calculate the next, and return the current one in the sequence. And as I said, really up to you. Usage also looks pretty much the same. I mean, it's times because it's a function call, not .current, but still nothing has changed much. And again, we're going to make it interesting by synchronizing this time. And if you want to synchronize enumerables, obviously you don't have any control over that interface or how sequences work in the runtime. Here you have to create your own sort of wrapper. Again, I synchronize enumerator of t, should be disposable. In this case, I'd say I just have one get next, gets you the next value, or the default for t, and a bool if the sequence is done or not. So this is the actual generic solution. And we're running out of time. In general, I don't expect people to read this. I just want to get people a sense of how involved this is, because now I need to implement this interface that I defined. It needs to wrap the enumerator that is passed in. It has to do some locking. There's a lot of stuff going on. Whereas in functional, well, good question. This is, again, the original solution I showed you. Show of hands, who thinks I need to change anything? Yeah, it's a trick question, because this follows the same pattern. No, I don't need to change anything. Let's again think about what's the very core of what I'm trying to achieve here. And the core is I have some method that is not synchronized, and I want to run this whole thing in a synchronized way. So let's just create a function that lets me do that. And this is where now also kind of as the big finale have a function that takes a function and returns a function. So here I very generically say, I'm getting passed in a func that I want to synchronize. So I create a sync root that I'm going to capture in a closure. And the closure is what I return. And what the closure does is simply says, OK, let's lock on the sync root and call the func that was passed in. And again, optionality, if I need this or not, is now up to the caller. The caller can decide they want to compose or not. But if they want to compose, it's very simple. They already have create function. They just need to pass this in synchronized, and now they have a func of datetime that is synchronized. Done. And this will work for anything that we want to synchronize. So 1 minute left, and I want to see if we can get to questions. Basically, it's book recommendations. Two broad categories. There are books that focus on a language of choice and then explain functional in that context. So there is actually this functional programming in C#, very good book. And of course, there's one of F#, if you're also interested in learning another .NET language. And especially if you might leave this room thinking, oh, maybe I actually have a lot of code that is suitable for pure functional programming because it's scientific, it's finance, you're actually coding mathematical functions. That might be interesting. There's also grokking functional programming and grokking simplicity. Both, yes? That's very cheeky, but good point. Okay, there's another option. That's very cheeky of you. But I will consider adding to the slide deck. So you get a bunch of options. Before I was a little bit derailed here, the point here, those two focus more on functional programming, and that's just happen to use Scala and JavaScript as a language of choice for showing you how to do it, because at the end of the day, you need some language to actually use and, have code samples in, but they really focus on explaining what is this functional programming thing really. And with that said, we're 1 minute over, but maybe let's see if we can take 2 or 3 minutes for questions.
Any questions? Yes,
Yes, you had a question.
Let me get up to you.
Hello again. So my question, as I stated previously, is Rust's result type considered a pure function, since it returns either OK or error, and from that basically it switches, usually with pattern matching, how the code flows?
I would put it this way. This is a very common pattern you find in functional programming, in pure functional programming, simply because you don't have exemptions, or even if you have them, like in C#, you're not allowed to use them. So you need to convey somehow if an operation worked or not. And what you just described, this result data structure that is okay with the value or failed with maybe some error information, that is the way to go. So you do something similar in pure functional programming in C and other functional programming languages. I mean, that in itself doesn't mean you're doing functional programming just because you use results. But if you do pure functional programming, you will need to use that. I hope that answers the question.
Thank you.